This is a video to support the HVAC sizing layout design exercise that we're doing in Environmental Systems 325. Um, I'm just going to do a stream of consciousness, sort of go over some stuff. I will admit that I've been sick for a week, so I don't know how coherent this will be. Let me start by saying, first of all, remember these are videos. You should scroll through them, go to the part that's useful to you. I want to start with a little intro to basically say that what I'm trying to accomplish here with the assignments and the way that we're organizing this course is I want to see us applying the fundamentals that we've been learning. We spent a whole semester basically on fundamentals last semester, and we've been talking about various fundamentals this semester also. And then I never see these really applied in a way that's anything more than just a couple of boxes, very vague layouts, if at all. And then I don't see it carried through in very often in studio projects. So what I'm trying to do is find the best way to make it real world and say, all that stuff we were talking about, heat movement through envelopes. Well, here's where it's applied because we have to have an envelope, and that's causing us to have a certain amount of heat loss, which is going to change our peak heating and cooling load, etc. Right? So there's a huge amount of information here. We are architecture students, not engineering students, and we're definitely not engineers. So this is too much for you to get in one take, and it's too much to take in and really understand holistically. But I think this is a good way to get started and to not make it completely abstract. So that's the goal. Okay, so what I'm going to do here is look at the Asheville Middle School project that we use as a case study in the slides. Remember, these slides are posted on Canvas, and that's the idea. They're supposed to be looking at the slides. We're giving you lots of resources like the plan sets for both the mechanical plans and the architectural plans for this project so that you can review these and try to understand better. If you don't spend time on this stuff and you just show up to class and you then spend a couple hours in the assignments, okay, you're not going to get that much out of it. You'll get something, and maybe you'll do okay in the class, maybe get a C. I don't know, but I'm just saying that's not the idea here. The idea is that you really should be spending time on this and trying to take a first stab at understanding how this works. And we're giving you the resources to do that if you will spend the time. Okay, so we have this project, and the advantage here is that we already know what the mechanical system is. So if I go to the slides for this week, which would have been what? This week, we, at the end, I think, there was a little summary slide where we talked about that we already know how large the equipment needs to be. We have equipment schedules that I then went and found the equipment that's in the schedules and shared some manuals with you that are on in Canvas that you can look at. You can use them for the design you're doing for this week. And we know how the engineer decided to lay out and design this mechanical system, and we went through it in some detail. We basically have roof-mounted AHUs. That we talked about, they look like something like this, and that we talked about in some detail how they work, and that they're connected to, they have energy recovery ventilation. They're connected to a heat exchangers that are tied into boilers. Get down to that. A boiler and chillers that are boilers inside a mechanical room, the chillers are outside. Anyway, we had a whole week on this, and so we know what the design for this project is. And so what I did is and so that gives me the advantage as I'm trying to model this in a way that I can get start to understand a sizing and a layout for the design. I already kind of know it, so I think it's a good way of dissecting this process. So what I did is in Climate Studio, I built a basic model that's attempting to approximate the project. I know the sizing from the plans. Now, I don't really care how accurate this is. This is a process we're going through, so I didn't spend a ton of time on it. I'm not claiming that it's accurate, but it's way more accurate, I think, than going into the Architect Studio Companion and just looking at that single chart that purports to allow us to size pretty much anything. Um, and it's way better than not having anything or just having a box that says HVAC, which I've seen a number of times in studio projects. Okay, so that's the idea behind this. Let's just be relaxed about it. We're not trying to make this crazy complicated, but we're trying to learn something. So the first thing I did is I just basically modeled a building using the square footages, and this you should have a model much more detailed than what I have for the project that you're working on for this class. Um, I have a saved view that I can always come back and see this from the same point, no matter what layers I have on. So that's something I try to do. I have a pretty organized model, which like I've been talking to you guys about. I have a site that I brought in. I really am not using this site for this, so I'm just saying that I did it. And I modeled several versions of this building. So the first one I did, and let me go to my thermal analysis. Oops, sorry. Oh, I see what it is. By the way, you probably don't know this. There's a drop down here, the eyeballs in the thermal analysis. There's three different settings or ways we can look at the model. The first is just the zones, which show us the opaque white surfaces and anything that's glazed, which will be blue. We can also look at the space use as defined. This has only one space use template. That's why it's only one color. And we can also see how how we've laid out the HVAC systems, because there's different systems we can choose. Right now, I don't think there's any HVAC systems chosen for this. Okay, so what I did first was I just modeled the project and into a single zone. So that means I don't have any floors. I have the volume somewhat accurately about the building, not even that accurate, but somewhat. It's we're faced. We have a climate file. Let's remind ourselves what's in the climate file. That's going to be related to. So what are we going for? We are, and again, I'm going to be rambling, so you just have to scroll through it, use it as you can. I just felt like I needed to do a video because I know this stuff is new, and also there's some professors teaching this that maybe are not as up on Climate Studio or whatever. So I'm just trying to do a service here. Okay, anyway, what we're trying to do first is model the building in a way, first of all, that we can just understand it and think about it, but we want to get a peak heating and cooling load. And the reason for that is because the peak load is what's going to determine the size of the equipment that we need, right? And so a good process would be to get your design, and if you've done this a bunch and you're later in your career, you'll already have an idea of a mechanical system that you think that the engineers are going to want to use, or you can model something like this at a basic schematic level and start understanding. Oh, you know what? I think I'm going to have to use this kind of system, which means I'm going to have a certain, I'm going to have a area for large ducts, so I need to think about that as part of my schematic design. That's the idea behind this. Okay, so what do we need to know to get to our peak load, heating and cooling load? Well, first of all, we need to know the climate. So we're in the climate, and remember, in Climate Studio, once we've chosen a climate, there's a bunch of information that's available in this climate summary. We're in climate zone 4A, which is the same as New York City. This is in Asheville, North Carolina, but it's still a different climate, and so we have different. If you bring in New York City climate files, you'll probably have different design temperatures. Remember, we said these are the temperatures to which we're saying when we do a simulation, we're saying think of this as the lowest temperature that we need to be able to supply heating for, and this is the highest temperature, 88 degrees. These will be different in New York City, and these are set by standards, and we're not going to get into the basis of that, but you can imagine if we're running a simulation, those design temperatures are going to have an effect on the peak heating and cooling loads, right? If we say, I need to experience temperatures that are 0 degrees Fahrenheit and heat to have a system that will be able to heat when we get that low, that's going to be a different system than if we're saying, no, the lowest temperature I need to worry about is 18 degrees Fahrenheit. And remember, the idea here is that if we wouldn't design, we need to design a system that's going to experience the peak heating and cooling loads, but we don't want to design it for every single hour of the year. So you can see right here, this is 0.04. There's 4/100ths of the number of hours of the year that are below this temperature. And we're saying, you'll wear a sweater. We'll have a secondary, under people's desks, we'll have little space heaters or something for those. Or maybe these hours are probably going to be at night. And if it's a school, there's not going to even be people there. So that's the thought process behind it. But the point is that our climate, that's from last semester, passive, right? Our climate has a lot to do with our peak heating and cooling loads. And so we're defining those variables in this simulation just by choosing a climate file. All right, so now we have a basic volume, and what about this building then, besides the fact that we know that we have a maximum and a minimum temperature that we're going to be designing to, what features of this building are going to determine the peak heating and cooling loads? Well, let's just look at this super basic model that I've made and think about that. So first I'm going to go to my zones, and we see that I've got one zone. I'm calling it whole building, and there's a lot of settings here, and sometimes it could be that people would say, look, we're just, this is the first time we're doing this. Let's just design, let's just be general about it. This is general, right? That all we're doing is looking at variables that we've talked about already, right? And this is bringing them together in a format that is actionable to apply to an actual building so that we can get a design. So this is real world stuff, but we've covered all these things. So if I go into, there are two templates in Climate Studio. So Climate Studio is saying this is a thermal analysis we're going to do. And so there's a bunch of variables that, hold on, I have to pause because there's somebody at the door. All right, I'm back. Okay, so Climate Studio has two template types that separate out the variables that we need to define in order to do a thermal analysis of our building. And by the way, we're not doing the full thermal analysis. We're just getting a peak load, peak heating and cooling load, and then we're going to use that for sizing. And then next semester, we'll do a full detailed energy analysis. Okay, so I'm going to click on this library button right now, just to introduce the idea of templates. So we have zone use templates and zone construction templates. And the first thing to notice is that, well, there's a bunch of them. So actually, I'm going to go, so this is where they are. There's a ton of them. And what they do for us is they allow us to have a set of presets for different situations that would be related to our design. So we don't have to go and look in ASHRAE 90.1 and know all about it to understand, what a climate zone 4 envelope, roof envelope, what the minimum insulation is required. There are templates that we can choose that will have all these presets. But if we don't understand the background to it and we can't look into the template and make adjustments, then we're not learning very much, first of all, and then we're also not, we're in danger of creating mistakes, right? So let's delve into this a little bit. But realizing we can also just choose these, click a button, go, and we're done. So there's a range here. But I'm actually going to go, so what I did is if I select, actually I'll just make a separate one right now just so we can quickly make a point. If I make a volume and I call it a zone, this template window opens up and it says, okay, what template do you want to apply to this zone? Okay, so it's automatic. And inside here then I can say, well, yeah, I have, this is a school, so I want to only look at school templates, and then I can go to a drop down here, or I can actually open up that library window again, and I'm filtering my templates for education here. I can pick a standard if I want to. I could say just ASHRAE 90.1 or any standard. And then I can scroll through and find templates that work. And so these are zone templates, right? We're saying, because what if we said a zone is? A thermal zone is simply a box of air that has different or has specific heating, cooling, ventilation requirements relative to another box of air that's next to it, right? And so it's going to have different requirements for our HVAC system based on where it's located, the people that are using it, the equipment inside it, etc. Okay, so we can choose a template that relates to our situation. So I'm going to get out of that. I'm actually just going to delete this. So I chose for this one giant single zone, which in some ways is cool because we can do it quickly. I'll make that the case in a minute that it's not the best way of doing this. It's too simple. We can get too complicated. We can be too simple. We want to find the sweet spot in the middle. Okay, so now I'm going to come over to my zone and I'm going to edit. I'm going to look at my template by clicking this little icon here. And so this is the one I chose. I'm going to edit that. By the way, okay, actually, I'm going to go. This is. I think I have adjusted this. This isn't the original one that I chose. So let's go to. I'm going to edit this completely. Go to Education, any standard. I'm going to scroll down. There's one template for schools that is whole building. I'm just going to choose that, and then I'll talk about why I did that. And NECB is a Canadian energy standard. Canada does have Canada's much colder than the United States, but it does have a climate zone that is like our climate zone in New York City, 4A, so we can use their, at least it makes sense to use, in other words, from a climate standard, we can use standards from Canada also. So now I'm going to edit this and look at what's inside of it. Okay, so now we're in the space use template with these presets for this National Energy Board of Canada whole building template for a school. Okay, so let's look what we have here. We have loads and we have conditioning. In loads, so what are loads? We're saying what's adding heat or energy use to the building. These are let's call them passive loads. So people will add heat, right? Because we are little combustion appliances, so we have to set a people density, and this is in people per square foot. 0.012 is that's people per square foot. So 1 divided by 0.012 is 83 square foot per person. Now, I don't want to get into a lot of I'm kind of going to ramble on this a little bit because it can be long because you can scroll through it. But I'm also not going to. I can't teach an entire class in one video. But this is not occupancy. So one place you could say, well, okay, where would I get a number that tells me how many people I want to say are in my building or in this zone? Well, I could look up occupancy tables for egress in the code, which we've done hopefully before. But that's actually a maximum number of people because we're doing that for egress purposes. Like what's the most number of people that we're allowed to have in this type of space use to then design the egress system. So we don't use that. And there are places we can find this. Like this is, we could use the ASHRAE 62.1, which is that ventilation standard, which there's a slide about in one of the lectures. We could maybe use 90.1. There are, because ASHRAE 90.1 is where we get our energy code. We'll be talking about this. But we can also use our and the best thing we could use is if we were working on a real project and we were talking with engineers, we'd want to use actual numbers. We'd want to estimate based on our desk layout how many people we have in this office, we think, or based on a specific aspect of our school design that we would use our intelligence to plan a number of people. Or we can use a template. And so what's going on here in this template, and the reason I chose a whole building initially, what they're doing is saying we're going to take a school and how a school is used, and we're going to find an average, or we're going to choose a number that will allow us to have a single space use for all the different types, space types, stairs and corridors and classrooms and the cafeteria, and just have one number so that we can just quickly do a we can do it a quicker energy model or a quick calculation. So that's what this number is. So we could pick a different number. It doesn't matter right now, but I would stick with one that you pick in a template. That's fine. But that's where it's coming from. The metabolic rate, that's how fast people are moving around. 1.2 is a good just default to leave because it's 1 would be completely stationary, essentially comatose. 1.2 is moving around. It's kind of office level. It's a good just baseline. Of course, if we were in a gym, we would change this. If we want to get much more detailed, that's why we'd have individual zones, and we would say in this particular space, we're going to have this kind of metabolic rate. We also always have occupancy schedules. We could leave this as all on, or this again in a template. This is an occupancy schedule that they've created that's got some kind of gradation based on. Let's find an easier one to look at. Just like if we just here's a straight up one that makes sense. We're saying that the people are not there until 8 in the morning, and then they're there all day, and then they leave it at 6 in the evening. I mean 8 in the evening. Sorry. Wait. No, this is where my sickness. No, that's 6 in the evening. Okay. Anyway. Okay. So the point being that we can set a schedule that would then determine how often the people are there, which is going to determine how much heat is being let off by them, right? Airspeed we can leave as it is. Just 0 is fine as a default. Then we also have equipment. This is the equipment power density is, this is in watt per square feet. Make sure that you're using IP units in this class, inch pounds, not SI. So the equipment power density is how much power is being how much power is used per square foot. So it's a way of, rather than having to specify all the equipment, you just use, there are these accepted standards for different situations. And so this is a pretty low power density. So they're generalizing because, you don't have any in stairs, you're not going to have any in corridors. If this were an office, it would be 0.7 probably. If it's an older building, it could be 1.5 for certain, if it was a data center, it's going to be very high. But anyway, so these are using energy. They're letting off heat also, and we have a schedule for these, or we could say all on. Let me show you, by the way, sometimes the most basic for any of these is just to say that it's on all the time. So that's kind of that would be the most extreme usage. Effect of equipment. Lighting power density is the same thing. How much lighting per square foot in watts. That means that how much power it's using. We set a luminance target for that. In other words, we're saying based on the usage of the building, we're saying that this lighting is going to deliver a certain amount of illuminance. We've talked about illuminance, and the main reason this is here is because we can also dim, which we're not going to do. I'm just explaining this whole thing. And so if I turned on the dimming based on, let's say if we had a big south-facing room, and whenever we met this, reason why it's 46.468 is because that's a conversion from a metric standard. This is in foot candles, so it's a conversion from lux. If we were in an office and our desk surfaces were the sun was out and we were getting 46 foot candles on the surface or more, then we could set the dimming to turn the lights off or dim it. And that way by dimming it, then we could say, well, we're getting 35 foot candles. Let's just dim the lights to where we're getting 48, but we're not using as much power. So that's why that's there. There's also a setting for hot water. So if this is off in the general, in this general template, if we were talking about a classroom, it would be off. If we were talking about a mechanical room or a locker room, it would be on. And then we'd be looking at the settings for hot water and how much water is flowing per person, etc. Okay, so that's the the loads that we're experiencing in the building based on people and equipment and lighting. Um, then we have to set our conditioning schedules and ranges. And so I'm going to. So we can either set a schedule, or if I just put it on constant. Um, so in this template, our heating set point is 68 degrees. That means when it's below 68 degrees, we're going to turn the heating on. And our cooling set point is 79 degrees. When it's above 79, we're going to turn to cooling on. In our, and this is, I realize, is what has changed. Let me get out of here. Hopefully I didn't change this yet. If I go and edit the actual setting here, this is probably why. Yeah, right. So now I'm in the actual template that I used for this simulation, and I've got 72 and 75. And the reason that's true is because in my design documents for this project, they had chosen 72 and 75 for the set points. So I'm trying to make this accurate to the project. Okay, but then we could also set a schedule if we wanted to. Now, the temperature set point should turn the heating on and off when we get to those temperatures. So in a way, we don't necessarily need a schedule, but schedules. There are schedules that change the set points. So like they say, okay, well at night we don't really. If it's winter, we can let it go down to 65 degrees, or you know, or there's other things that a schedule will adjust. Okay. In addition to the set points, then we also have to. So let's go back to our definition of a HVAC system. The set points are going to be for heating and cooling, so that's our source of thermal energy. We have to distribute. That's not what we're talking about here in terms of, well, actually, we're not. We're the whether or not we're distributing that heat or cool through air or through water or refrigerant is defined in the when we define the mechanical system. I'll show you that later in this what's going to turn out to be a very long video, but you're going to scroll through and use this at your leisure. But here we're talking about fresh air ventilation, and we're saying how much air do we need per person, and how much air is the building going to require to air it out based on what's the use of the building. And remember, we talked about this in actually, I think there was even there's a better slide that actually pulls these out, but they're from this ARCH325 62.1. We have charts that tell us what the CFM per person, cubic feet per minute per person, that's required in different spaces, and also the outdoor air rate for the building itself. And so let's not get any more into that, but you can see, for example, here in this animal exam room, the first one up here, it's 10 CFM per person and 0.12. So it's the same as this interestingly enough. Point is, we're setting this because we talked about this in previous weeks, right? If we're going to be bringing in fresh air, that means we're going to be exhausting interior air because we have to be balanced. We can't just keep putting more air into the building or taking it out because it's we need the same amount of air in the building at all times. And that's going to cause us to lose energy, right? So we're going to have our nice 72 degree heated air inside, and then it's 25 degrees outside. If we bring in some of that air, it's going to be a considerable heat loss as we dump the 72 degree air out. That's why we use some kind of energy recovery ventilation. And that can be set in the mechanical system. But right now we're just saying, okay, this is how much air we're moving, and that's going to have an effect on our peak loads. Okay, so that's these are the variables that we're setting for the space itself, the space use, and the volume of the space. The other template that we mentioned was the construction template, and that's right next to that. So I'm going to edit this one now, or look at it. I'm just going to dive right. Well, let's go back in here again. I can pick in the if I'm filtering for education. You guys might be filtering for residential. If you're doing your apartment buildings, there's or you can just say any building type and get the full list. I'm going to go back to educational. So in this case, I don't have specific space use because we just talked about that. So it's going to be really be the whole building, and so this in this case we'll probably mostly have just one template being used for the entire building. I'm going to select secondary school CZ4 because I am a secondary school. It's a middle school in Asheville. CZ is climate zone 4. That's what we're that's where we are. And so let's look at the settings here. So first, I've got a bunch of now, and I'm remembering we've been over some of this. Definitely in class, I've been over all of it, I think. But quickly, there's slides about these things. But I want to have a resource that you can refer to. So sorry if this is redundant. So the first thing that we're looking at in our construction settings is the envelope. And you'll see here that we've got these, our entire building envelope is set here, and it's all 90.1. 2019 is the closest, the earliest, I guess, we have, or the latest we have in Climate Studio right now. They're set to non-residential, climate zone 4, exterior roof. That would make sense for a school. And these little icons here are showing us what part of the building is being defined. And if we click on any of these, we have a section. This is actually from UBACUS, or these values at least are from UBACUS. And we have these preset envelopes for 90.1 for our climate zone that meet the code. And so if you go look in the code, you'll see that the R value, I think it's in this case for a commercial building with continuous insulation on the roof, it's about R30. And so we've got R31 here. I mean, that's the minimum, it's R30. If we go look at the walls, it'll be similar. We can look it up in the code and it'll be reflected here. So we're just meeting the bare minimum of code with 9.1, it looks like in this case. Sometimes they may go higher for some reason. And then we also have a description of the section here. So it's they're saying felt. I think that's really probably a waterproof membrane. This is translated from some other language maybe. Insulation board, concrete, and then acoustic tile underneath. Okay, we can also copy this by selecting here, and if we copy it, give it a new name, I've got a bunch of them down here that I've copied in the past, and we can then set whatever, we can add whatever layers we want, and define them, how thick they are, and create our own envelopes. So I want you to eventually, before the end of the semester, to have created your own envelope in your model, so that we are, when we do run a peak load simulation or whatever the final requirements that we're going to determine, you'll have your actual envelope in the model. Anyways, right now we can leave it like this. We've got our presets. What else do we have in this particular dialog? We have infiltration. So this is the amount. This is how airtight the building is. We've talked about this before. We have 4 control layers, right? One of them is air. We have vapor, air, thermal, and liquid water. This setting is very low. This is for a commercial building in using 90.1. I think that the code in New York City is you have to be at least 0.25. That's the energy code. 0.1 would be probably a good level. So 0.045 is just a very well designed building. It's also, though, since it's a larger building, this is the CFM per square foot. That's square feet of exterior surface. And so if you have a big volume, you'll have less surface area, and so it's easier to meet this a lower number. If that's confusing to you, don't worry about it. I'm just saying that obviously, though, so let's go back. How our envelope is arrayed, like how much insulation we have, if there's any breaks in the insulation, etc., will have a big effect on how much heat we gain or lose, right? On our energy performance of the building, heat loss, heat gain. And also, though, let's say we have a really well insulated building, but we've got a bunch of gaps in it, so there's air moving through, and we're losing heat or gaining heat in the winter or the summer that way through the building envelope, then that also will have a large effect on our energy use and therefore our peak load. So this number is very important. Okay, so that's the envelope and infiltration. The second tab, settings, you can just leave those defaults, so I won't even click on it. Windows. We can set I need to go back and remind you that so these are all the faces on this model are set at 0.4 window to wall ratio, which means 40% glazing. That's the highest you can do by code, but of course many buildings have more than that. We've talked about that. Don't worry about it. You can do whatever you want, whatever you think matches your project. But so right now it's default glazing. That's not what I would have wanted. Let me click on it. I'm going to type in 90.1. Oops, I didn't mean to hit enter. 90.1 non-residential, climate zone 4. Climate zone 4. Not skylight glazing, non-metal. Let's just pick that. We see that, and if you look it up in the code, these are basically the bare minimums for U value, solar heat gain coefficient. That's the maximum solar heat gain coefficient. And TViz, that's pretty low, 40%. But if we select this, then that becomes the glazing for all of anything that we're calling glazing in our building envelope. So obviously then we need to know the performance level of the opaque envelope and of the windows and the air tightness. The rest of the stuff in the windows you can leave. You can turn the frame on or off if you want to. That's going to change your we can set the conductance value of the frame. We talked about conductance last semester. Ventilation settings is going to have to do with natural ventilation. You can just leave the defaults. It's fine for now. And the shading system, just leave it whatever it has there. Okay, so that is our construction template. And all of that was automatically set when I chose, well, actually what I did is I went and adjusted a little bit, but I could have chosen a single zone, whole building, had the presets, and run the simulation. So I did that, and let's look at my results. So now let's just talk about this for a minute. There's a lot of really great information that we can get when we run a thermal simulation. How much energy use, our energy use intensity, which is energy use per square foot. We have this great energy flows chart that we've talked about before and that I will talk about in a lot of detail next semester. But I'm not even going to worry about that right now because, and you don't. So I wouldn't even right now look at your site EUI, which is the most direct measure of the efficiency of your building, because we're not talking about that. We're talking about just what the peak heating and cooling loads are. And so we could have, this is going to be very affected by the efficiency of our mechanical system, right? So we're in a catch-22. We got to put in a mechanical system to get these outputs, but we don't know our mechanical system yet. So we do have to set that in order to get values, but just ignore those for now. All we're concerned about right now is our peak heating week and our peak cooling week. And what these are showing us that the highest number on these weeks are our peak load for this model. Okay, let's just look at our, what was the load that our engineer told us that they were using? Let's see if I can find that quickly. Yeah, here. So they've got a peak heating load of 5,000 MBH. That's the same as kilobtus per hour. 1,000 BTUs per hour is what that stands for. And then we've got a cooling load of 400 tons. So we're at about a little over 2,000 and about 160 for cooling. Now, like I said, I'm not worried about how accurate this is. We're going through a process here. Everything we've talked about so far in this already pretty long video, which is only half over, is important information, and we're accessing it by applying it to this simulation. It doesn't matter how accurate it is. But why might our loads be different than what we're seeing here? Well, the most obvious reason is because we do have a volume that's somewhat related to the volume of this building. I tried to model it like that, since I made this a single zone, I got rid of all the floors, so we don't have anywhere near the square footage that we would have had. So that's going to affect our loads. So that's one thing that might be happening. But we do have a heating and a cooling load, and so in a way we're done. We could just move on to our sizing if we wanted to, but we're not going to do that yet because there's still more to talk about here. I'm going to switch now to talk about the different ways I modeled this building. So we already said this is the most basic, the single zone. I also modeled it as sort of to approximate the buildings that are described in the way they laid this out. Remember here, the A, B, C, D, E, F. Um, I divided the building into those zones because I was thinking, I know that in terms of the actual design of this project, we've got, let me go to the roof plan. Oh, that's I need the mechanical plans. We have these AHUs in the roof, and so I was thinking, yeah, can I kind of approximate that and figure out the best way of um, modeling this so that I can actually use this concept of the way that the actual project was designed. Um, so when I ran this one, this is, let's see if I know my, by the way, I have notes here. This is a good thing to know. You can add notes. Um, BDS is buildings with floors. So this is the full buildings one. CB is, okay, I'm going to talk about that in a second. IDL is ideal air load. CB is condensing boiler. I'll show you that next. But the point is now with this, I have modeled the building now with floors. It's the same volume pretty much as the last one, or maybe exactly. I think I just copied. I think I might have done this one first and then combined zones to make the other one. I don't remember. But the reason I now have a very different, everything else is the same except now if I go, this was the original 2195 for heating load, and in this version I'm at 4895, so much more. I think that the cooling loads are much closer. We could try to surmise why, but still, oh, actually no, it's 450 and 160. So that makes sense. It's just we got a lot more floor area, and if we look at we're much closer to the actual numbers, right? We were at, and again, that may just be luck. I mean, we're just kind of playing around here, but we're at 450. For the cooling load, we were 390, no, 400. That's pretty close, right? And for the heating, the peak heating load, we were at 488.95, and where 5,000 was their peak load. So we're incredibly close. So I think we kind of lucked out here because this is not a super accurate model, but showing that by some iteration, using our common sense and what we understand, we can get what seems to be closer to what the actual the engineer who designed this found. But what's this other, so these are the zones or the geometry, the whole building or the divided into buildings. What's this ideal air load CB? I'm going to go to, so here I am in my I've got my my climate data. We talked about these. This is the primary energy where electricity is much higher than natural gas. But then if if we're using heat pumps, we have really high efficiency, high COPs, and so we can get, it's actually lower for electricity than for natural gas. So we're not dealing with that right now. These are all, if you pick a heat pump, it's going to automatically use electricity. So this is all internally linked in Climate Studio, but that's what that tab is. We've been working in this tab, the zones. I guess I have to turn on. Oh, I have to scroll over. This one I have all the, so these are floor 1, 2, 3 for building A, floor 1, 2, 3 for building B. And these all have, you'll notice, these have the same, they have the whole building template that I actually changed the number of people here. I changed the equipment, so I did play around with it based on my knowledge. I set the set points to the same amount. I mean that the engineer designed, and I think mechanical ventilation of 10.12 is good for schools. So this is me using my a little bit higher expertise than you to set this. But the point is, I've got a single space use and construction template for, in this case, I'm just using the 90.1s, and I do have I have 90.1 glazing. Okay, so we've been over all that, but what's this final tab? The mechanical system design. By the way, I created all these. So we have 4 different options here. We have the ideal air load, VAV, DOAS with FCU, DOAS with VRF. We've talked about all those. So again, wow, that's interesting that these slides tie into the practical real world. We actually even the drawings we had were from Climate Studio, and we made the basic point that the VAV is heating, cooling, and fresh air is all going through air. But with the DOAS, it's direct outdoor air system. That means that we're only bringing in fresh air. Um, we're only moving air to bring in fresh air, and that we're either bringing heat or cool with hot water with the FCU or with refrigerant with the VRF, variable refrigerant flow. So I was playing around, and you can just bring as many of these as you want to in, and you can edit them and change their settings. So we're going to keep it simple or I kept it simple for these simulations that I'm talking about here. But what's going on? There's really two basic approaches that you can take, and I would suggest you start with the ideal air load. And this is a concept they came up with in Climate Studio, which I think is pretty cool. And I'm gonna edit an ideal air load. Con boiler means I've got a condensing boiler, but you don't see that. All that means is the default typically for this would be 0.8. That's just their default. If you go look at systems for boilers, so this is heating COP. We talked about COP. We're saying that. So I'm saying my boiler has a COP of 0.87. I chose that because that's what when I go back and look in the equipment schedules that I found for the project that were specified in the plans. That's all in this. Like we have schedules here from the plans that specify equipment. Train CSAA for the air handlers. This is a train condensing unit. This is this Luckenvar boiler. So I got these from actual equipment manuals. And anyway, and I think this 0.87 is listed somewhere else in the plans as the actually it's probably listed here in the hot water boiler. Yeah, 87% efficiency. All right. So what we're doing here, though, is then we're setting a conceptual mechanical system that doesn't have any ducting or delivery system. So we're just saying we're designing a system, and the simulation is going to run as if it's just sort of magically putting the temperature that's needed into the zone. It's going to be its efficiency is going to be determined by the settings we have here. Like, and so the reason this is natural gas, we could pick a different one, and that would have a different primary energy and a different carbon footprint. But we're not going to worry about the complexity of modeling ducting, and that's just an energy modeling trick here. If you want to, you can definitely you can bring in these other, and I would definitely do that on a simpler model. What might happen is if you start bringing in, if I try to emulate the system for this project with 15 roof-mounted air handling units, each with their own heating and cooling system that I set custom here, I think it's going to break the model. And I don't really need to do that. That's not what I'm trying to do. I'm trying to get a peak load. So I think using the ideal air load is fine. Now, you might talk to an engineer and they'd be like, no, you can't do that. But we're in a class. We're just trying to get something that we can use. So I'm totally happy with it. But let's keep talking about it. So I'm defining the COP of my heating system. I can change its fuel type. I can say if it's I can create a schedule for it. I'd probably leave those as all on because remember we've already set the set points, so we're already turning on the heating and cooling based on set points. This would be a more complicated approach. You can play around with it, but I don't think we need to right now. This number right here, this 1.15, this is saying it's the heating sizing factor. We're saying we're going to oversize by 15%. Because you always have to oversize. This isn't an ideal world, and we're approximating everything. So we could set this higher. I guess we could set it lower. But that's what that number is. The maximum supply air temperature is 95 degrees. This might need to be higher. Well, I shouldn't say that. If you look this up, like as a rule of thumb, typically you see 100 to 120 for heating, just like ducted heating supply temperatures. And again, this is ducted here. I would leave it that way, but I would also play around with this, and I'll show you why that this has a meaning a little bit later. Okay, So that's the heating system. The cooling system has a COP of 3. Now we could go lower if we wanted to, a little bit lower. We could also go higher. Remember, cooling is always going to be, active cooling is always going to be a refrigerant cycle. That means it's going to be moving heat rather than producing it, or like by burning a fuel. And so we can have we can put in 1 unit of energy and get out 3 units of cooling, and that's what we're saying. Always going to be electricity here. If we're well, I guess you could switch it to others. That'd be interesting. I guess if you're off the grid or something and you were trying to, yeah, you could create your own electricity to run uh, your heat pump, I guess. Um, then again, we have the sizing, and then the minimum set point temperature is 53.5. I typically see 55 for this as a rule of thumb, and I would have put this at 100 or maybe even 110. But these are fine. So this is showing me, yeah, I get this at least, and we'll see why in a minute. So this is why these have an effect on our sizing. Um, but what we're saying is that we're delivering air of this temperature when we're cooling, and we're delivering air of this temperature when we're heating. Um, let's just go ahead and say why might that have an effect? Well, no, let's wait. Just remember that we're going to be talking about that. Humidity control, just leave this at the 80 and 20. This is just saying if we were to get outside those zones, we would. I'm not actually even sure how humidity would be added. I guess it's just there's a piece of equipment that's then added to add humidity or subtract. I don't know because we have other ways that we can deal with humidity, like in energy recovery ventilation, which is so the mechanical ventilation section of this ideal air load that does not actually have ventilation is just saying, do we have energy recovery? In this case, there is none, but I could select sensible or enthalpy. Hopefully you know something about what these are. Sensible would be an HRV. Go back and look at the slides. Enthalpy would be an ERV, and the enthalpy is going to be transferring both sensible, so air temperature, and humidity, relative humidity in the air between the two air streams, the fresh air coming in and the exhaust air going out. I'm not going to talk about economizers right now. We'll just leave the fan pressure limit, and we're not going to use natural ventilation. So what we're saying here is that this is just, we can adjust these. So I did adjust slightly, and I went from the 0.8 to 0.87 because that was what was in my specs. So I could do more. But I'm going to then, or what I did in this simulation was I used that ideal air load condensing boiler for all of my zones. So that means that I assigned zones. I selected all of these. I said okay, and I ran it. Now it's really important that let's say you close your model and you open it up again, and you're going to work on it some more. Just always check that, because sometimes it seems like Climate Studio just turns off the HVAC system sometimes when you close the file and open it up again. So if you make a run that doesn't have any, if you're looking here and it doesn't have any heating or cooling loads, or it's got you may not be able to interpret this right now, but if you didn't have any heating or cooling loads in this energy flows chart, it means you didn't apply a mechanical system. You can still often get outputs, but they're useless. So make sure you have mechanical systems applied. So when I ran this one with the ideal air load condensing boiler, these were the peak heating and cooling loads I got, which are here in this whole building section. Okay, what else do we want to say about this? Oh, maybe I'll just talk about some other ways that I modeled this. And this is important because once we finish sizing, which you actually were supposed to have done last week, but this is really a 2-week assignment. I may even go a little longer. Remember, let me throw this out there. The way I'm looking at these weekly assignments is, you don't turn it into 0. You turn in something that you took a shot at it, but you didn't do all of it. It's 5 points. If you turn in something that tried everything and it looks like you understand the basic concept, you get a 10. But that does not mean that you did. Some people do great work and other people do decent work, and both people are getting a 10. Why would you do the great work? Because this is your final portfolio, which I think is worth 25% of your grade. And so if you kind of half-ass it week to week, when you get to the end, yeah, you maybe have got 10s on those assignments, but you're not going to have really anything that's useful for your final portfolio. If you do this well, your final portfolio is basically done at the end of the semester. Anyway, that's how I'm That's how I'm conceiving of it. Okay. So how else did I model this? Well, I did. Let's even just look at a different model. So you may remember. Let me see if I can find. Um, when we were talking about zones, yeah, it's right here. I threw up this slide, um, and and this is where again, this is a lot of information. It's hard to know what's the when I'm giving you too much or just how to approach it exactly. But um, you know, you're going to be if you were designing a mechanical system, your zones technically are going to be what are the portions of the building that have a unique set of heating, cooling, and ventilation requirements. I'm going to have to make that a separate zone, which just means I'm going to have a way of delivering different HVAC requirements to that zone. It might just be um, like in this system, we have these VAV boxes so that I can, as long as I got a duct going into a room and I got a VAV box, I can probably adjust so I could have one branch duct with 15 of these VAV boxes coming off it, and those could all be zones because I can adjust the temperature coming into the room or the area with that VAV box. Um, so zones are that they are space use, and they're relative to how people are in spaces, and they're definitely going to be enclosed by walls typically, or a series of walls. But another way to look at zones is how they, and this is very important, but it's kind of an overlay, is how the building is situated um, on the site. And so, for example, this is a prototype building model from ARCH3 90.1, and they're saying so. Like for an office, they've got what's the slide above. There's like 25 of these that have different concepts of how you would split up zones. And so in this one, in an office, they're saying, okay, at a minimum, you're going to have 5 perimeter zones. They're going to come in 15 feet from the exterior wall, and that's because um, one reason is because for daylighting. That's gonna be like the first limit on or it's um, a typical measure of a daylighting zone where that you have a clear definition of how much light's going to be getting in there based on its facing of the building. But also, each of these exterior walls is going to have a different amount of heat loss through it based on the amount of sun hitting it, right? So you definitely would have then a south-facing, a north-facing, and a east and west-facing zone. And if you're already heating and cooling, and so in the winter in a cold climate, this is going to be a lot warmer over here on the south than on the north, and so you can have different heating, cooling requirements. That's a different zone, right? Um, Once you're heating and cooling these 4 perimeter zones, then this core kind of becomes the same, right? I mean, if you're not thinking about how many people are in there or other things, how much equipment, because it's buffered by these 4 zones. So it then becomes um, this buffered ambient zone that's going to have a different thought process in terms of how you're going to heat it and cool it. So that's the idea behind this. Now, I played around with that in this model. I did do a perimeter zone model. It doesn't really make sense to me because there's just so much different going on in these. And then here, this like central building, there's just a lot more going on that makes it much more complicated. Um, and there's really there are no like this is mostly stairs on the side. Anyway, so but I ran it and I played with it. But in this project would make a lot more sense. And this is based on this DOE sample. I've got an open office. This is a 3-story building. It's got repetitive, or actually it probably should be much larger. There should be a lobby that has a different layout. But we've got offices. Some of them are open, hot desks. We've got assigned offices. There's a conference area in the middle, and then a service core where you have your stairs and your elevators. So this could actually make a lot of sense to zone in that way, right? Because now I've got the offices on the outside it just makes sense in terms of the layout of the building that I might use this zonal approach. So my point here is that then as I'm thinking about zones for a given project, first of all, it's going to take practice and playing around, and a lot of architecture to me, especially as students, is playing, having fun, getting into it, saying, wow, what does this do? And then the cool thing about simulations is you can run them and then see what the effects are when you change things. Um, so I did that with this other project, but it doesn't really make sense. Other things I did was I don't even really remember. Oh, plus I found that I have to turn these off before I turn them on again, or it takes forever. Let's see. Come on. Bear with me here a second. There we go. Yeah, so I did a thing where I made a more complicated shape. I did the actual, the layout more of the gym. I added these bump outs. I did that where I had, so that one I think I didn't. Yeah, so but I didn't have corridors or anything there. I was still just thinking in terms of the zones for the AHUs. But then if you look at the plan, there is ducting and the corridors. So I did one where I was trying to simplify it so it wouldn't take so long, because these can take a very long time if you have a lot of facades. But that doesn't really make sense for the same reason as the first one, the massing one. There's just too much. There's not enough floor. Um, this one I think worked well, and I got some decent results from it that I'll look at in a second. But let's look at, so this is all the zones, right? And if you look at actually I'll switch to, let me go to, this is more really thinking about space use, and so you see it gets pretty complicated. I can do this drop down and go to these are color coded now for the different space use templates that were used. And so these greens are all classrooms. I went ahead and combined them together because, again, this is all classrooms along here. Some of this is still simplified. I've got corridors, I've got stairways, I've got bathrooms. Um, Bathrooms are consistent throughout corridors. This is a cafeteria. This is a kitchen. This is a mechanical room that I think wouldn't have a mechanical system applied to it. Um, and so with these, then I could go in and pick specific templates that I use, and maybe then even updated. So for example, if I said, okay, I want all of these things to be classrooms, I could select these zones. Sorry. They show up here. Then I can edit them at the same time, and I could apply that classroom zone. And you see that if you look at these, so it's a different number of people. And again, this is all coming from 90.1. I don't from the energy code, so I don't need to. In a classroom, I've got a pretty high equipment usage. Lighting was what I had set before. The illumination target's much lower. I'm not sure why that's true. That's interesting. So I don't know the rationale behind all these if I were to look through it, but I might change it. I might go, I don't really like that. Let's see what they have for conditioning. They do have the same conditioning. Interesting, that I'd set before. Maybe that's where I got it. I don't really remember. Okay, but the point is here that I went through and I did organize all of these in my model into the specific space uses, and I did apply them. Now, again, if I were to go and try to apply different mechanical systems to all these, I think it's going to break the model. I could try it, and there's nothing wrong with trying it. Always save. If if you're crashing out or if it's taking forever to run, just stop it. If you totally crash, just close, open again. If you've just saved it, then it's not a problem. I always, before I run a simulation, I try to remember to save it. But I've also got my saving settings they save pretty often, and there is a place on your hard drive where crashed models go, and they're saved to the most recent, at least, setting time. Okay, anyway. But then, so even if I don't use this in the simulation, I can now start using this as a thought process for how I'm going to lay out my actual HVAC system. All right. Okay, so that's how I did all of those. And let's just look at results. This is with all the, I think this is only with classrooms. See, now I should have taken better notes on this. But this has a higher peak heating load, much lower cooling load. That's interesting. I have to go back and see why that seems to be true. Oh no, these are the perimeter. So these I don't think have any meaning. These are the ones that were just using this template here. Let's see if I have this is I think closer to the actual one. 200 instead of 400. And then the peak heating load. 5475. So that's pretty close. So this is an interesting one that I could also think about and use for my as a well, at least it shows me that I seem to be in the right direction. I'm not doing anything stupid. But oh, and also, how did I get that? What was my mechanical system? I can see here that I did set it to the ideal load combustion boiler. And so I might want to play with that to change it. But again, it is true that different settings, especially in space use, because in the space use, if I change the ventilation settings for different, like in most templates, your stairs are going to have zero ventilation because they don't really think of it as people being in there. And so the corridors and the stairs are going to have zero ventilation. That's going to lower your ventilation rate, which is going to give you a lower peak load. So there's things to play around with here. But okay, clearly that is enough on that. I've covered, and basically what I've covered right now is week 1. This is really all about the peak load. So what I'm going to do is I'm going to stop this video and do a second one for this week's assignment, which is the sizing and layout of the equipment. All right, so I'll see you there.